So we're back again, just waiting for everybody to get back in. So we're going to go on for another 40 minutes straight, and then it's going to say that it's stopping, ending the meeting again. So let me set up. While you get in, let me set up. So you were here. Okay, there were a few more people since a while ago, so let's wait for them. So we should have about 5 more people. Make sure no one is messaging me and see if anybody's messaging me in the WhatsApp group. Okay, 11, still missing 4 people. I saw 15 a while ago. Okay, I'm going to continue because the majority are here. Okay, I will just review the first 2. So we said we have 5 factors affecting disinfection. The first 2 having to do with the microorganisms. 1, the type of microorganism, because the type of microorganism will determine what the organism is made of, what's the outer shell or the skin of the organism made of, and that is going to determine how effective our disinfectant will be. The age of the organism, as some organisms age, the outer shell, some bacteria, for instance, the outer shell becomes tougher as they get exposed to various things in the environment. Also, based on the phase in the life cycle of the organism, different phases give different characteristics to the organism. And at some phases, the organism, like Giardia and Cryptosporidium, may be more susceptible to disinfectant, but at other stages, it may be more resistant. 3, water status or the water content. When choosing a disinfectant, this is one of the factors that we must consider. What is in our water? What chemicals? Do we have iron? Do we have manganese? What are some of the chemicals in our water? Is our water very turbid? Do we have other little particles or things that are in our water? Of course, some of these things will be filtered, but as you see when we go through later, you will realize that, especially with chlorination, we may add chlorine at points at the treatment plant before we actually doing our quote-unquote proper disinfection. Okay, temperature is another thing we want to consider. With most chemical reactions, as the temperature goes up or as it increases, the rate of the reaction increases. So the reaction happens more quickly and sometimes more violently as the temperature goes up. However, if the temperature gets above a certain point based on the disinfectant, the temperature itself could actually start to destroy or break down the chemical that's being used to disinfect. So temperature can be positive, but it can be negative. If where we are treating is very cold, the rate of reaction is going to be much slower. Okay? So it will take longer. We'll have a longer what we call contact time, which is the very next item. And contact time is an idea of a combination. It's a combination of the concentration of the disinfectant and the amount of time that we have whatever we are disinfecting exposed to the disinfectant. Okay, so that's what contact time is. There's actually some calculations associated with that, which we are going to look at in our next class. Okay, so do we have any questions so far? In our first couple slides, we've actually covered quite a bit. We've looked at the different types of microorganisms. We looked at the life cycle of Giardia and Cryptosporidium. We looked at some of the diseases. We looked at pathogens. We looked at disinfection, a definition for disinfection. Okay. We made a distinction between disinfection and sterilization. Yes, Ezekiel, you have a question.
Yes, when you say about the temperature of the area that we are disinfecting, the colder it is, the longer the contact time will be.
Mm-hmm.
When you say the temperature, you mean you're talking about the area, right? Not the temperature of the water.
The temperature of the water.
So the cooler the water is, the longer the contact time will be.
The longer the contact time, yeah. It is like, look at it like you're cooking, right?
Mm-hmm.
If you have a slow fire would generally mean that you're putting less heat into the pot that you're cooking, okay? So which means your temperature could generally be lower if you have a slow fire. But if you have a fast fire, the stuff will cook much faster. Come look at possibly cooking an egg on the little burner on your stove as compared to putting the egg in a big fire outside. The egg will cook faster in the big fire outside as compared to a little burner on your stove. The big fire outside, the temperature is going to be much, much higher. As a matter of fact, the egg might even explode. Okay, you know, if you leave an egg, was it a student or a colleague of mine? He had forgotten 3 eggs in a pan on his stove, and the thing dried out, and he was there watching TV, and he just heard the explosion, like when the eggs pop because they get too much heat. So if we apply too much heat, as the more heat that we have or the higher the temperature, the faster this chemical reaction is going to happen. Here's another example. Everybody here, I assume, is familiar with the phenomenon of rusting. I assume everybody knows what rusting is, where we have a piece of iron. Sometimes it's your tools, and after exposure to the environment, moisture, chemicals, and so on, we start seeing rust. It happens in our vehicles too. We start seeing a rust build up on the iron. Now imagine that same tool. Now this takes a period of, for the entire thing to rust away, it might take years. Okay, for us to see some rust on it, might take a few months. But imagine if we took that same tool and we had it in a hut, and the hut caught on fire and the hut burned down. The rusting would be accelerated considerably because we just increased the temperature. Okay, I was at a site yesterday, a site where there's a burnt house, and there was a fridge. I remember the fridge before the house was burned. The fridge was fine. The fridge did not have any rust in it. But the house burns down, and then the fridge, the metal from the fridge, is just a stack of rusty metal. But it was not like that before the fire. Okay? So the fire accelerated the rusting, or the corrosion is another word that we use for that. The corrosion that would have taken place over a period of years in that fridge. Okay? Over a period of maybe 10 to 12 years, then you would start seeing some rust in here and some rust there. But in a day or in a few hours, the entire thing just became rusty because of the increase in temperature. And that's what we're really looking at. Okay? So we clear? Any other questions? Okay, all right, great. So let's move to our next slide. So you have to remember these 5 factors and the explanations as to why they're important to disinfection. Okay. So types of disinfection. So we've looked at what disinfection is. We looked at the factors that affect disinfection. So now we want to look at some of the types of disinfection. Now we can group them, you know. We can group them into 2 groups. We could either have chemical disinfection or non-chemical, or sometimes refer to it as physical disinfection. Okay? With chemical disinfection, we have chlorine, we have chlorination, we have chloramination, we have chlorine dioxide, we have ozone. So these are all chemicals that are used. Now, as I said earlier, I'm not going to go into every detail of these because it's nicely covered and properly covered in a video, in particular on the platform. So I advise you to look at the video so that you could learn a little more of this. You will notice though that at least 3 of these things start with chlor, okay? Which means one of the active ingredients in them is chlorine. When we talk about chlorination, we're looking at chlorine gas, calcium hypochlorite, or sodium hypochlorite. These are the 3 forms of chlorine that we usually use for chlorination. The chlorine gas requires a lot of special equipment because it's a gas that has to be pumped through a line. Okay, so the chlorine gas is probably among the different forms of chlorination, it's probably one of the most dangerous because chlorine gas is a pungent gas. It's a greenish, yellowish kind of gas, and it can cause a lot of damage. Now, in your household, I'm not admonishing you to try this, but at your home, if you mix, I don't even know if I should say that, but we have adults here who will not go and try foolishness at their home and send themselves to hospital. Okay, but if you were to mix your chlorine bleach, if you were to mix chlorine bleach and an acid, the acid could be vinegar. One of the byproducts of that will be chlorine gas. That's why they advise you, if you read on the chlorine bleach bottle, you're advised not to mix it with any acids. Imagine you cleaning your bathroom, and a bathroom is usually an enclosed, you could look at it as a confined space, most bathrooms, except for probably those of the very wealthy. Okay? But most bathrooms are confined space, and imagine you doing some cleaning, and a lot of people are starting to use vinegar as a way of cleaning around their house. Imagine mixing chlorine and vinegar in your bathroom while you're in there trying to clean with possibly no personal protective equipment. A lot of Caribbean people don't like to use personal protective equipment. So they might have a little pair of gloves, and that's maybe it. So you may not have any breathing aids or mask, respiratory mask, and chlorine would be released in that area, and it will take quite a while for it to clear. You would feel your nose start to burn, your eyes start to burn, because it's a very pungent, it's corrosive, and that is mixed the moisture in your nostrils and in your eyes. It's going to burn the skin that's there, the lining, okay? And depend on the amount of time that you're exposed to it, you may have a problem in the long run. Okay, I remember, and we have to be very careful. We have to speak about safety as regards these chemicals. I remember I worked for a number of years. I worked at the community college here in St. Lucia, the South Louis Community College, as a chemistry lab technician. And yeah, I had some adventures there. And one time we were doing an experiment where we were using some pungent organic chemicals, and we told the students that they should not leave. They were using conical flask. They should not leave this conical flask on the stand above the Bunsen burner, but they should hold the conical flask and like just pass it through the flame. One girl decided that she was leaving it because I'm not sure why she left it, and this thing ended up heating up, and the gases from it, I just heard a sound, and when I looked up, I saw like a mist coming down. That time I had a pair of glasses. not protective glasses, but glasses on my eye. And this mist just came down, man, on everybody who was close to her. And then you just felt your skin start to burn because the gases that she was using, they were corrosive. And as they met the moisture in the skin, they dissolve in the moisture and form little acidic substances, which is what happens when you dissolve chlorine in water. It forms an acid. And the acid is, well, it forms two acids. And these acids are basically what is responsible for the disinfection that takes place. But that was quite an experience. And it taught the students seriously why they should be careful when using chemicals. And if you work in a chemistry lab and there are other people using the lab, sometimes things happen to you. I remember somebody had used, one of the students had used a station, and acid fell on a stool, and the stool was never wiped by the student, and somebody went to sit on that stool, and of course they had a hole. That person ended up with a hole in their pants. It seems funny now, but at the time it was not funny, because what if there was enough acid to get through the person's pants and to their skin? Okay, that means the person would have a burn, and based on the type of acid, different types of acid might leave different types of burns based on how concentrated. Some acids will just burn your skin and basically leave a kind of a hole because it chars the area that it comes in contact with. Okay, and so dealing with these things, chemicals, if you ever have to use them, for instance, when you're doing chlorination, you must wear the protective gear that is provided. Okay, next one is chlorination. That's basically a mixture of chlorine and ammonia. That is usually made on the spot as you need it. And that's another disinfectant. Chlorine dioxide is a substance that has chlorine and oxygen in it. And the next one is something totally different from chlorine. Most of you would have heard of the ozone layer. Ozone is basically a molecule that has 3 oxygen atoms in it, and it behaves totally different. Regular oxygen has 2 oxygen atoms, ozone has 3. So that's a 1 molecule. So it behaves a bit differently from oxygen. It can be toxic. Most times, if you're using motors, electric motors, there's a certain scent that you take. That scent is actually ozone. And if it builds up and the amount of ozone is concentrated, it could actually be toxic to human beings. So there again, you will, from what I have said, you realize that a lot of the things, the chemicals that we use for disinfection are actually either toxic or corrosive. So they require you to use personal protective equipment. So these are the chemical disinfectants that we use. Chlorine is one of the first option here, chlorination. It's one of the more popular chemical means that's used for disinfection. So let's look at the other category, types of disinfection. The next one is non-chemical disinfectants or disinfection. And we have 2 things under there. One of them we've mentioned before, heating or boiling. You will notice I have striked through it because it's not, boiling or heating is not really feasible. It will cost too much money to try to boil thousands or millions of gallons of water a day. It will just cost too much money. It's not practical. So UV or ultraviolet radiation this is actually a very popular one. It's usually used in a lot of developed countries. They use it as a means of primary disinfection, which is what we will discuss next, primary and secondary disinfection. Okay, so in some of these places, it's used for primary disinfection. And basically what it is, if you looked at the video again, I encourage you to look at the videos. Basically what it is light, basically. Some of you may be familiar with UV the idea of UV from some of these forensic detective shows where you have the forensic scientists coming on the scene and they have this light that they use to look for human hair or look for organic matter from persons and so on, semen, blood, and so on. They use it sometimes if a murder took place in a particular room and the person tried to scrub it down so that you're not seeing any blood, the turning off all the light and using the UV light will show you where blood was on a carpet or on a floor and so on. So it's used for these applications as well. But that same UV light, of course, at different intensities, is used to purify the water because these microorganisms, as they come in direct contact with UV, they are killed. So it actually destroys them. So what we use is a series of bulbs or lights. So they usually have a system where you have a series of bulbs or lights. It's set up so that all the water that passes through comes into direct contact with the UV light or the UV rays, and you have your disinfection happening. Now, I want to say something about that because most of the disinfectants that we have discussed, especially the chlorine ones, have what we call a residual. Okay? We have some way of ensuring that we have a certain concentration that remains in the distribution system to maintain disinfection. However, ozone, I believe, and for sure UV light do not have residuals. And this is why in most treatment plants and water plants or distribution systems, we do not use all these solely, or we don't use them alone. So we might use ultraviolet light or UV for primary disinfection, ozone for primary disinfection, and we have our chlorine for secondary disinfection, okay? Because we want the residual, and we're going to discuss what's the purpose of secondary disinfection as well. Okay, but all of what I have spoken about here is mentioned in the little video on the various types of disinfectants. I am not sure if we have any questions right now. So if you have a question, you can use the raise your hand feature and I will answer your question. Okay, so let's move to our next slide. Okay, so in our next slide, this slide just looks at some of you may not be familiar with what happens in a treatment plant. So I just wanted to have a little diagram to just show one of the things that happens while we're going for an earlier slide, I mentioned that water treatment has various components. We have coagulation and precipitation, then we have filtration, and we have disinfection. So these are some of the components or some of the processes that take place on the treatment. Now, if you look at the diagram here, we have our water coming from a river, okay? So the water is taken by our raw lines, our intakes, and it is pumped in some instances. In other instances, it goes by gravity. When it goes by gravity, we just mean that the water is flowing by gravity, gravitational forces, natural forces. So if we cannot get it to the treatment plant via gravity flow, then we get it there with the aid of pumps. Okay, so when the water gets there, the water might have what we call turbidity. And when we talk about turbidity, we are talking about suspended particles in the water. In most instances, these suspended particles will give the water a cloudy appearance. Okay? So we will add things like alum and other chemicals to cause what we call coagulation. in the water. And when we coagulate, what we are basically doing, we get in these suspended particles, these fine particles to clump together. Okay? And when they clump together, they are going to come out, basically come out of solution, and then we can filter them out. Okay? Because they have clumped together, we have larger clumps. Okay? Then once we have done that, we filter, or in this case here, we have a settling basin first. So that's pre-treatment. We have a settling basin, so the coagulant, the clumps are going to settle to the bottom, and then we'll get this water out. So that's the first stage. Then here we have what we call a cold filter, charcoal filter, with sand at the bottom. So charcoal at the top, sand at the bottom. Our water then goes through this filtration process. Now this filtration process, based on how fine our filter is here, we may be able to filter out things like giardia and cryptosporidium. We may be able to filter them out, as well as other particles that may be in the water. Okay, so after it goes through here, it filters through this specialized sand, and then it goes into this hidden bridge reservoir where we add in chlorine. If you notice, we add in chlorine at this point, where our disinfectant rather, and the water gets here. Then the water leaves our reservoir, that's our storage, as post-treatment. So treatment is happening here. Okay. Some treatment is also happening here. You realize we add disinfectant, and we're going to discuss these in a while. Okay. There are several points in our system where we add disinfectants, and we're going to discuss them. So once we get here, the water goes out and is pumped or goes via through gravity flow to our consumer. Okay, so we may add different types of chemicals here. We add in sodium hydroxide to control corrosion. So sodium hydroxide basically is what we call an alkaline. Now don't mix that up with this thing that's going around in health diets, where people are talking about your blood has to be alkaline and so on. And people get crazy and they drink all kinds of strange things trying to get their body alkaline. Okay, these things are not meant to go in the stomach. Okay, so we add it to the water to prevent corrosion. Okay, corrosion, rusting is an example of corrosion. So if we have iron pipes, adding the hydroxide, making the water slightly alkaline or making it less acidic, will decrease the rate of corrosion. Okay, now I'm saying a lot. If you have any questions, you can ask. Okay, so I wanted to point out, so you know about your coagulation, your filter, okay, and the place where your disinfection happens. I want you to point this out so that as we go through the next set of slides, you will have a better understanding of what we are saying. So we have what we call pre-treatment, we have filtration, we have post-treatment. Okay, you will notice that even in pre-treatment, we are adding our disinfectant here. In post-treatment, we will add disinfection between the consumer, disinfectant between the consumer and the point of disinfection. Okay, so let's look at the next slide, which is going to discuss some of that. So points of application of chlorine. So I'm pointing out things that we do with chlorine because chlorine is one of the, well, I could say that is the most popular form of disinfection that we use in the Caribbean. Okay, so pre-chlorination would add water, we would add chlorine at raw water intake to control zebra mussel. Okay, and zebra mussels, this is something that belongs to the same family as snails. They come basically two flat shells kind of stuckish together, and on one end there's a muscle that controls of whether they open or close. Okay, you would have seen them most times if you go by the river or sea. You'll see a lot of them clumped onto rocks and so on, or onto concrete areas that remain in contact with water. We also use it for biological growth control. One of these can be algae, which we have not mentioned. Okay. I have a little 10 minutes again before this thing shuts down. Okay, so let's see what we can cover. So raw water intake, the flash mixer, okay, which is an area in the treatment plant where we have something like a fan that mixes the water, and there we add some chlorine in there, and we add it so that we control the amount of iron in the water, or the form in which the iron is in the water, and manganese. So what we want to do is we want to try to oxidize them. So we want to get ions and manganese ions. Now that might sound a bit confusing, but if you did science at school, you will know that an ion, I-O-N, okay, do I have a marker? No, I don't. Okay, I don't have a marker. I was looking for a marker. Okay, but I-O-N, okay, refers to particles that are either positively or negatively charged. Okay, so we might have Fe2 plus or Fe3 plus. These are two forms of iron. And manganese, I think, is 2 plus, Mn2 plus. Okay, so we change them from the metallic form to ions. Okay, and most times we will get iron chloride and manganese chloride. Okay, and we can precipitate these things out if we need to get them out of the water. Okay, so for oxidation, and here we have turbidity and odor control as well. So turbidity we mentioned earlier, and odor control. We don't want to give people water that smells stagnant. So that's why we have odor control. Remember in our first class, we looked at the aesthetic qualities of water, and we looked at what has to be controlled. Odor was one of them, temperature was one of them, turbidity was one of them. Okay, so, but turbidity is special because the particles that are suspended in the water actually do two things. They reduce the effectiveness of our disinfectant, because the disinfectant must react with whatever is in these particles first before it can actually deactivate the microorganisms. Okay, so and these particles, when you have turbidity, these particles offer shelter to pathogens. So if we do not have the right dosage of our disinfectant, we will not kill these pathogens. Okay, so for the filter influent, in other words, the point at which water is coming into the filter, and I showed it to you. That was the first point. If I were to go back, okay, if I were to go back here, that's our filter influent. Okay, we can look at it from here too. So we add in chlorine before the water gets to our filter. Okay, so let's go forward. Okay, and you will notice for some of these, I'm giving you the point at which chlorine is applied, as well as why it's applied. Okay, so at the filter influent, we want to continue to control bacterial growth. If you've gone to if you've ever gone to a treatment plant, you will notice at some points in the treatment plant, we may have a lot of algae growing. Okay, we want to control the algae, but we also want to control things like bacteria and other forms of life that may be in the water. They may not be a source of, they may not be pathogenic. In other words, they may not be directly cause disease, but they may harbor things, they may harbor pathogens or protect pathogens. So we want to control them. And they may impact other qualities to the water. For instance, algae, some algae might impact taste properties to the water. And you might have your water tasting a strange kind of way. So we want to control these things. We don't want the water to taste like it's stagnant water we send into people's pipes. That would be a problem. Okay, and as I mentioned, stagnant water. In fact, when I get to that point, I will mention it. Okay, so post chlorination. So at the clear well, Here, the clear well is where we store in our treated water. So we may have to add some chlorine here to maintain our chlorination, our chlorine residual, sorry, to maintain our chlorine residual in the tank. So chlorine, so clear well of chlorine contact tank. So when we talk about the contact tank, we're talking about disinfection there. We're going to leave the water, hold the water for a while until we can ensure that we have proper disinfection and we have moved towards our residual. Okay, and in the distribution system as well. Okay, in the distribution system includes points where we have a repair or we have a construction or an extension of the distribution system. We would have to disinfect here as well. Or if we do a test and we realize at some points in the distribution system, our chlorine residual is either low or non-existent, then we will have to add chlorine at that point as well. Okay, so these are some of the points. So we looked at about 5 of them. Well, more than 5, about 8, sorry, of them. Okay, so breakpoint chlorination is an important topic. You will notice some time was spent discussing it in the videos. I'm not going to go through it in detail. I will attempt to simplify it. We have a chart here. Okay, so I will just attempt to simplify it for you. So if you look at the chart, this orange line is our curve. Our vertical axis, which tells us how much chlorination, how much chlorine residual we have. And our horizontal axis looks at the chlorine that has been added. The chlorine that has been added, we can look at it as our dose. Okay, so the chlorine we've added here, the chlorine residual. Now you'll notice chlorine residual is almost 0 for the first section of the graph. Okay, as we add chlorine, the first thing that starts out, the chlorine dissolves in the water, it forms 2 gases and 2 acids. And these acids begin to react with things in the water. So here we have a lot of reaction taking place. Okay, so we have reaction with iron, manganese, nitrites. Then we have reaction with organic material, and the reaction with organic material is creating these non-ammonia trihalomethane is also an important byproduct. Monochloramine. So these we get as a result of reaction with organic materials. So here we have our residual starting to go up, but you notice it goes up and then it comes back down. It comes back down because it starts to, the free chlorine starts to react with some of the byproducts of chlorination. And it starts to react with them and it breaks them down. Okay? And so our residual takes a hit here. But then it goes back up after we have passed at this point, break point here is when it starts to go back up, which tells us that we have reached the point where our chlorine has deactivated all the pathogens, has reacted with everything, every piece of organic matter or otherwise in our water. And so our residual starts to go up because there's nothing else for our chlorine to react with in the water. Okay. Now, this session is going to end again, and I'm going to restart it. I think I'm going to just go ahead and restart it now, and I'm going to return to this slide when we get back. So I'm stopping it now, and you will just join back again for me, please. I'm sorry about that. I'm hoping that this issue is solved by next class.